Hi everyone, today we are going to talk about our last part of activity 36. We're going to talk about solving systems equations, especially larger ones, using our calculators. So we can see in front of us we have a three-variable system, x, y, and z, and we can set this up in our matrix equation format where we have the coefficient matrix, the variable matrix, and our constant matrix. So this one is in nice standard form for us. We have this three-variable system, x, y, and z, and then equaling our three constants. And we know that when we have a, x, and b, this equation, in order to solve for what x actually equals, we need to take a inverse times b. So we're going to make sure we have this entered in our calculator. I have these pre-entered to save a little bit of time. But if you need to pause and make sure you enter, we have matrix A. We also have matrix B entered in slot 2. And then if we take our matrix A inverse times that matrix B, we have our output value, which we usually like to write if it's not a terminating decimal as a fraction. So 13 thirds, 2 thirds, and 2 thirds. You get that by just math, enter, enter as your final solution. And we've talked about a little bit, a lot of times you will see these represented either in that matrix or as an ordered pair, or in this case, triple. So we have 13 thirds, 2 thirds, 2 thirds representing x, y, and z as coordinates. Now we can do this for even larger systems. In this case, we would have A, B, C, and D. So notice on this first one, we have 1A plus 1B minus 1C. Notice there are 0 D's. So you still are going to have to account for that when it comes to typing this into your system. Same thing here. We have 0 A's, 1B minus 1C plus 1D equals 2. A is 1, B is 1, C is 0 this time, D is 1 equals 5, and then 1A plus 0B minus 1C plus 1D equals 4. Okay, so sometimes it's nice to have that because especially as we set up this coefficient matrix, we have 1, 1, negative 1, 0, 0, 1, negative 1, 1, 1, 1, 0, 1, and 1, 0, negative 1, 1. And again, this time we have officially A, B, C, and D we are solving for, equaling our constant matrix 3, 2, 5, and 4. Negative 2 from over here. So again, I have these pre-typed in. I typed them in mine as C and D, but we have a 4x4 matrix that you will want to enter in. Again, making sure all of those are correct. And then we also want to make sure we enter in matrix B. I'm entering it in the D slot just because I had it pre-put in. We have 8, negative 2, 5, and 4. So this time I'm just going to select option C again is my A inverse this time, times D, which is acting as my B this time. Just had it pre-typed in. And again, whenever they do not give us super nice numbers, math, enter, enter to get that variable system solved. Okay, so we can really see the convenience here of a matrix equation to solve because by hand this would be a nightmare to try and solve, but instead we can solve for A, B, C, and D rather quickly. Now in example 3, we have P, Q, and R that we are solving for. They are 1, negative 1, 1, 2, 1, negative 1, 1, 2, and negative 2 to solve for P, Q, and R, and that will equal 0, 3, and 1. So again, as we start solving this time, okay, I typed these in this time as E and F in my calculator, and if I take E inverse times F, my coefficient inverse times my constant, notice I'm getting an error message as my output. It's a singular matrix error. Now, why is that happening as we try solving for A inverse times B? We're getting error. Well, if we check out the determinant on this one, if we take the determinant of that matrix, in this case, we had that in as matrix E, we see we have a determinant equal to 0 for that coefficient matrix. So the determinant is equal to 0. So what's going to happen, and this is very important to note, is that when the determinant equals 0, that's giving you one of two options. Either no solution, because these lines are parallel and they never intersect, or what's going to happen is there are infinitely many. And a lot of times why this will happen is if you can transform one of these equations to be another one, like your coefficient matrix, for instance, could transform into the other one. So we would be having the issues kind of coming there potentially for that. All right, try example 4 on your own. See what you get as your output values for A, B, and C. Now we can also use the system of equations and solving with the matrix equation to again help us when we have these bigger systems, especially more than even 2 variables. So this time we have a small furniture company making tables, chairs, and bookshelves. So I'm going to call this T, C, and B for tables, chair, and bookshelf. And we are trying to maximize our efficiency. So we know that we have 165 hours available for assembly, 205 for finishing, 90 for packaging, right? That's kind of our total hours. So our table and it takes 2 hours, our chair takes 1 hour, and our bookshelf takes half an hour for assembly. So basically, if we kind of line that up with the assembly aspect, we would have 2 hours per table, plus 1 hour per chair, plus 0.5 hours for bookshelf, and that has to add up to be 165. And then we have the finishing time, so we have 1 hour per table, 1.5 hours per chair, 2 hours for bookshelf for finishing. That is allotted 205 hours per week. And the last part then is our packaging time. It takes 1 hour per table, a half hour per chair, and 1 hour for a bookshelf for a total of 90 hours on that. So we have our original system, and we know then that we could set this up as a little matrix equation, this time a 3x3, setting up T, C, and B, and what the best type would be to actually solve on this. So if we take, we have, our A, X, and B, coefficient, variable, constant. Okay, this time I have this plugged in as options 7 and 8 as our matrix equation. So we see here the first matrix, we see here for, again, option 8, G and H for these. So A inverse times B, this time I'm going to use G inverse times H. And we see our final output, 27.5, 105, and 10. Now, the problem with this is I don't really know how you're only making 27.5 tables. So maybe they either find a way to only make 27 or round up to 28. But that's what their maximum, if they can use 27.5 tables, 105 chairs, and 10 bookshelves, that's going to be the best use of their time to maximize based on their timing. All right, last one is for you to try. This time we have foods A, B, and C. They're carbs, proteins, and fats. You want to set up a system and an equation and then ultimately solve for how many servings of food you should have for each meal plan for the food A, B, and C. Thanks everyone for watching. We'll finish these up in class.